All right, today we're going to tackle a concept that really changes the game in mathematics, the square root. Now, I know it might seem a little abstract, but it's actually the key to solving a puzzle that had early mathematicians totally stumped for centuries. So let's just dive right in and start with that very puzzle.
I mean, really think about that for a second. We all know 1 times 1 is 1, and 2 times 2 is 4. So, what number can you multiply by itself to land exactly on 2? It's not a whole number, and it's not some simple fraction you can just write down. This exact problem is what forced mathematicians to realize, hey, we need to invent a whole new kind of number.
And that mysterious number has a name, the square root. The definition is actually pretty simple. It's just the reverse of squaring a number. The square root of a is just whatever number, when you multiply it by itself, gets you back to a. And we use this cool symbol called a radical to write it down. So the answer to our puzzle? It's simply the square root of 2. Now, to really wrap our heads around this, we first need to get a handle on its fundamental identity. What is this thing really? Okay, so here's a crucial detail that trips a lot of people up at first. Every positive number actually has 2 square roots, not just 1. Think about it for a sec. A positive number squared is positive, right? But a negative number squared is also positive. So for the number 2, we have the positive root of 2, and we also have the negative root of 2. All right, so now that we know what they are, let's dig into how they behave. You can think of these as the absolute rules of the game, the fundamental properties that everything else is going to be built on. What's so cool here is just how perfectly taking a root and squaring a number are connected. They're inverse operations, which just means they cancel each other out. If you square a square root, you just get the number that was inside. And if you take the square root of a number that's already squared, you just get the number back. It works like a charm both ways. So how do we get a feel for the size of a square root when we compare it to a regular number, an integer? Well, the trick is to put them both in the same language. Let's ask, which is bigger, the square root of 10 or the number 3? First step is to turn 3 into a square root. Well, 3 is just the square root of 9, isn't it? Okay, now the comparison is super easy. Since 10 is bigger than 9, the square root of 10 has to be bigger than the square root of 9. So root 10 is greater than 3. Simple as that.
The very existence of a number, like the square root of 2, kind of forces us to zoom out and realize that the whole world of numbers is much, much bigger than we probably thought. So where do these things actually fit into the grand scheme?
So up until now, most of us have lived pretty comfortably in the world of what are called rational numbers. This is basically all the integers, positive, negative, and 0, and any number that can be written as a nice, clean fraction. They're predictable, they're tidy, they make sense.
But here's the kicker. Numbers like the square root of 2 or even pi can't be written down as a simple fraction. Their decimals just go on forever and ever without repeating. So they don't really fit into our neat little box of rational numbers. So where do they belong?
And this leads us to the bigger map of the number world. We have to create a whole new category called irrational numbers for these values that we can't write as fractions. And when you put the rationals and the irrationals together, they form the complete real number system. So see, square roots aren't some weird outsiders, they're just part of a bigger family we hadn't met yet. Okay, enough theory, let's get practical. How do we actually do math with these things? Let's check out how to add, subtract, multiply, and divide them. Let's start with multiplication and division, because honestly, the rule here is super simple. If you're multiplying 2 roots, you can just multiply the numbers inside and stick them all under a single combined root. The square root of 3 times the square root of 5, that just becomes the square root of 15. And the exact same logic works for division. Just divide the numbers under one big radical sign. Easy. But, and this is a big but, addition and subtraction work completely differently. The absolute best way to think about it is to treat square roots just like you would treat variables in algebra. You can only combine like terms. And this is an absolutely critical distinction. You can only add or subtract roots if the number inside the radical is exactly the same. So just like 3x plus 5x equals 8x, 3 times the root of 2 plus 5 times the root of 2 is 8 times the root of 2. But you cannot simplify the square root of 2 plus the square root of 3. That's it. It's as simple as it gets. This is a huge, huge difference from multiplication, where you can always combine the roots. All right, we've got the basics down, so now let's move on to the final level, learning how to simplify more complex expressions, so our answers are always in their cleanest, most standard form.
The first key skill here is simplifying. The goal is to make the number inside the root as small as possible. And we do this by hunting for any perfect square factors. So for example, the square root of 20 isn't really in its simplest form, because 20 is just 4 times 5. And hey, 4 is a perfect square. So we can pull that 4 out of the root, where it becomes its own square root, which is 2, leaving us with 2 times the square root of 5. Next up is a process called rationalizing the denominator. I know, it sounds really complicated, but it's just a rule of mathematical etiquette. For a bunch of historical and practical reasons, it's just considered standard practice to never leave a square root in the bottom part, the denominator of a fraction. And here's how you do it. It's actually a pretty clever trick. Let's say we have 5 divided by the square root of 3. We just multiply both the top and the bottom of the fraction by that same square root. On the bottom, root 3 times root 3 is just 3. On the top, we get 5 times root 3. And there you have it. No more root in the denominator. So now we can build our final checklist for any problem that involves roots. Here's the order you want to follow. First, always handle any parentheses using the distributive property. Second, go through and simplify every single root in the expression and rationalize any denominators you see. Third, take care of all the multiplication and division. And then finally, as the very last step, you can combine any like roots with addition or subtraction. So after all that, what are the most crucial things to remember? Well, first, a square root is simply the inverse of squaring a number. Second, these are irrational numbers, and they're part of the bigger real number system. Third, you can multiply and divide roots pretty freely, but you can only add and subtract roots when they are like terms. And finally, always clean up your final answer by simplifying and rationalizing.
And that leaves us with one last thought. We didn't just learn a new way to do a calculation, we've unlocked an entirely new set of numbers. So the real question is, what can we do now? What problems in geometry or physics or anywhere else are suddenly within our reach now that we have this tool? Now that is the power of a new idea.